Have you ever wondered how a robotic arm knows exactly where to place an object, or conversely, how it anticipates its final position given a set of joint movements? The way we instruct and understand a robot's physical actions comes down to two foundational concepts: forward kinematics and inverse kinematics. You use forward kinematics when you know the joint angles of a robot arm and want to calculate the resulting position and orientation of its end effector, which is the tool at the end of the arm. Conversely, you use inverse kinematics when you know the desired position and orientation for the end effector, and you need to determine the specific joint angles required to achieve that target. The fundamental difference lies in the problem each method solves. Forward kinematics is typically a computationally straightforward process because it involves a direct mapping from joint space to Cartesian space, meaning from angles to coordinates. It always yields a unique solution for the end effector's pose. Inverse kinematics, however, is significantly more complex. It's a mapping from Cartesian space back to joint space, and it often involves solving nonlinear equations, which can result in multiple possible solutions or sometimes no physically achievable solution at all. To decide which to employ, ask yourself what information you possess and what outcome you seek. If your task is to simulate a robot's movement or to check for potential collisions based on its current joint configurations, you are working with known joint angles, so forward kinematics is your tool. For example, if you are animating a robot arm and you are manually setting its joint values, forward kinematics shows you where the end effector will land. However, if you are programming a robot to pick up a specific object at a precise location, weld a seam, or interact with a human at a given point, you already have the target end effector position and orientation. In this scenario, inverse kinematics is indispensable for calculating the necessary joint angles to reach that exact target. Understanding these concepts also introduces deeper insights into robot design. For instance, the concept of a robot's workspace often relies on forward kinematics to map out all reachable points by the end effector. On the inverse kinematics side, challenges like kinematic singularities arise when certain joint configurations cause a loss of degrees of freedom, making it impossible to move the end effector in certain directions, even if a target is technically within reach. This also relates to redundancy, where a robot arm has more degrees of freedom than strictly necessary to reach a point, leading to multiple inverse kinematic solutions. Ultimately, the choice between forward and inverse kinematics depends entirely on your specific problem and the goal you are trying to achieve with the robotic system. Both are indispensable, complementary mathematical tools that empower engineers and roboticists to precisely control and understand how mechanical arms navigate and manipulate the physical world, enabling everything from industrial automation to advanced human-robot collaboration.
If you love robotics, like, subscribe, and keep building with us.